Hi, this is going to be Lab 8, Sequential Logic Design. Let's do some analytical stuff for this. Draw the timing diagram and state diagram for the circuit in Figure 1 for varying Q values on the outputs of the 4 flip-flops, assuming the circuit starts in the state 0, 0, 0, 0. What does this circuit do? So we're going to figure out what states it transfers between, what states it moves between here. Okay, so we have 4 JK flip-flops, and it looks like we've got Q1, Q2, Q3, Q4, and they're hooked up in the opposite direction. So Q4 is the most significant bit, and that's the one over here. Q1 is the least significant bit, that's the one over there. All right, so the other stuff in here, we've got some high voltage supplies, and we've got a ground, which is hooking up to some other things along this this ground rail there, and we have some NAND gates which look like they are leading to the inputs of some of these flip-flops. So let's go through and look at what is connected to all of the inputs of the flip-flops here. So we have the numbering again is 1, 2, 3, 4. So let's look here. So J1 is equal to, that's just high. So that's wired to the 6-volt rail there, which is our high signal. So that's easy. K1 is equal to, so not K1 is equal to 0. You see the circle on this input is indicating that, like the flip-flops that we have in the lab, the K input is actually hooked up to K bar, not to K. So that means that K1 is equal to 1 all the time, which means flip-flop 1 is permanently in toggle mode. Okay, so continuing like this, it looks like flip-flop number 2 here, we have K2 is equal to so look at this. Not K2 is equal to Q1 bar. So what this means is K2 is equal to Q1. And what about J2? J2 is hooked up to this NAND gate. All right, this is getting a little bit more complicated. So we'll get our equation typing out here. Yeah, so J2 is equal to a NAND between, now what are the inputs to this NAND gate? It looks like Q3 bar, and the other input is Q1. Okay, so J2 is equal to, no bar on that, is equal to a NAND between Q3 bar and Q1. All right, so what flip-flop number 2 is doing is not obvious just yet. We'll have to leave that for now. Okay, flip-flop number 3, we've got J3 is equal to Q2, and similarly, not K3 is equal to not Q2, which means K3 equals Q2. So that one has an input which is just equal to Q2. So this one, J and K are going to be the same, and they're going to be equal to Q2. So this is either going to hold if Q2 is equal to 0, or toggle if Q2 is equal to 1. Right. All right. And the last one, we've got the 4th flip-flop over here. Looking at that one, K4. So not K4 is equal to, tracing this wire over, 0, which means K4 equals 1. And J4 is equal to this other NAND gate. So let's see, J4 is equal to a NAND between, what's the inputs of that gate? We've got Q2 bar and Q1. So both NAND gates have one of their inputs as Q1. they differ in the other input. So this NAND gate that goes to J4 feeds off of Q2 bar, but this NAND gate feeds off of Q3 bar. That's the one that went to J2. Okay. So there we go. Okay, now that's the inputs to all of the flip-flops in terms of the J and the K. The other things that we can look at are the presets and clears. So these are only going to be acting like flip-flops as long as the presets and clears are not doing anything funny. So we have not preset with the circle here. Preset would set it to 1 if this gets a signal, but not preset is set to high. So that means that we are going to be not presetting these flip-flops. So they're going to stay at, this is not going to be impacting the circuit. Okay, same with the clear. Not clear is also set to high voltage. So these inputs can be ignored. They're not going to be setting what the output is. Okay, the other thing that we need to look at, we looked at J and K. We made sure the presets and clears are not doing anything strange. Maybe we'll write that down. All preset and clear inputs, let's call them don't preset and don't clear inputs are wired to high, so have no effect on the circuit. Great. Now we looked at J and K, and the other thing is the clock. So the clock input is set to this this function generator here, which doesn't give the frequency. It also doesn't say what voltage it's at. So we'll give the question the benefit of the doubt and assume that this is at enough of a voltage to actually clock these flip-flops so that they do something. And the frequency will be variable. So I think, yeah, question 4 asks you to vary the clock frequency and see how it affects the output. So you can set it to whatever frequency you like in order to see things working. Probably you want no more than a few hertz in order to see the LEDs moving around. But for the limits of the circuit, we may have to take that up pretty high in frequency. Okay, so the clock is, the function generator here is clocking the input of this flip-flop, and it looks like it's also clocking this flip-flop and that one. So first 3 flip-flops, let's call them Q1, Q2, and Q3 are running off of the clock pulse from the function generator. However, Q4, while Q4 has a clock, let's say takes its clock pulse from Q3 bar, from not Q3. Okay, so in other words, since this is a positive edge clock trigger, since it doesn't have the circle, it triggers when not Q3 goes from low to high, i.e. when Q3 goes from 1 to 0. That's when Q4 is going to be triggering. All right, so let's start to trace what's going on with this circuit based on the information that we have here. All right, so to draw the timing diagram, there's a couple of different ways that you can think about it. So first off, what you can do is list out some variables here. So let's call it Q, well, maybe we'll put a clock right there, and then we'll put Q, we'll see what we need. So Q1 is always going to be toggling, so we don't need some extra information there to figure out what J1 and K1 are, because those are always permanently 1. So one way that you can write this out is you can start off with like a 0, 1, 0, 0, 1, 0, 1, okay, and think about it like that. Then we'll go Q1. It's going to trigger on every rising clock edge. So it's suppose that it starts at 0, then as this clock rises, it's going to go 1, and then it's going to trigger again the next time we have a clock rise, okay, etc. Oops. So let's try that. Okay, great. So there we go. And you could imagine copy pasting this out, that, and that. Okay, cool. Oops, there we go. Okay, so there's Q1. Q2 is a little bit more complicated because we need to know what J2 and K2 are at each instant. And in order to know what J2 is, we need to know what Q3 is, as well as Q1. So let's start off with, let's say, J2, K2, and then we'll have Q2. Then down here, we're going to put, let's see, J3 is equal to Q2. I guess since that's the case, we don't necessarily need another input for this. Well, it's probably clearer. J3, K3, and then Q3. Then we'll go J4. K4 is always equal to 1. So maybe we don't need to write. Okay, fine. And then we've got Q4 down there. Right, being very decisive here. So J2 is, we're going to need to know what the other outputs are. Now, we were given that they all start at 0. So what we can do is write out what the input is going to be, and we'll imagine that we're writing here the inputs sort of after this has become the case. So these inputs that we put here are going to affect the next state, yeah? So if Q2 is 0, if rather Q3 is 0, and Q1 is 0, then NAND of those two, NAND is only going to give us a 0 in the event that both of the things were true, right? So that means we're going to get a 1 for that. Okay, so J2 is 1. Now K2 is equal to not, so not K2 is equal to not Q1. So this is just equal to Q1. So I guess we can fill out all of the K2 states by putting that all the way there to the end. All right. So then we've got 1 for J2 and 0 for K2. So that's going to go making this next Q2 a 1. All right. J3 is equal to Q2 and K3 is also equal to Q2. So we can paste those all the way to the end. And that's going to tell us whether or not we're doing anything with Q3. So because we have a 0 there, we are not going to toggle Q3. So that stays at 0. And we'll continue on. J4 is based on a NAND between Q1 and Q2 bar. So as long as Q1 is false, then this is going to evaluate to true. And K4 is just equal to 1 all the time. So we can fill that out. All right, so there we go. Now just knowing J4 and K4 doesn't tell us whether anything is actually going to change next, because we also need to know about what the clock for that fourth flip-flop is doing. And that flip-flop takes its trigger from Q3. So it's going to trigger when Q3 goes from 1 to 0. So because of that, since Q3 was certainly not 1, then there's we don't actually care what J4 and K4 are just yet. So that's not gonna do anything. It doesn't get a chance to change to do any flip-flopping because we don't have any state change from Q3 there. Okay, so let's continue on here and try and get some next state information. Right, so J2 is equal to, again, the NAND between Q3 bar and Q1. So Q1 is now a true, and Q3 bar is also true, which means this is going to actually evaluate to a 0 next. Great. So with that being a 0, on the next rising clock edge, we can we can have something potentially changing. So nothing changes right here because we don't have a rising clock edge in that transition. So that's still the same there. But then on this rising clock edge, we have J2 equals 0, K2 equals 1, which means this flip-flop is going to do the reset mode. So it's going to go back down to 0. Okay, great. So next, Q3. We've already worked out what J3 and K3 are doing here. So because those ones are just tied to Q2, there's no change just yet because there's no clock. But on this one, where we have a rising clock edge, because the flip-flops were equal to 1, we are going to toggle Q3. So this goes to 1. And nothing depends on Q4 tied back, does it? No. So actually we can just ignore that and figure out what's going on with the rest of this table and then use that to figure out what's going on with Q4. Okay, so let's go back up here. J2, now that Q3 is a 1 and Q1 is a 0, that's going to be true again. In fact, both inputs to that NAND are going to be false. So on the next chance to change, which is the next rising clock edge here, we are going to be cycling from a 1, we have 1, 0 for J2, so it's going to go up to 1. And now both of these inputs, oh wait, now we can change what's going on with the next flip-flop with Q3. So this is the rising clock edge here. The inputs are 0, so that's not going to toggle. It's just going to hold. And we have information now to figure out what J2 should be. So the inputs are 1 and 1, which means Q3 bar is 0. So we're going to end up with a 1 overall. Maybe to make this a little bit more clear, what we can do is De Morgan's law this. That's Q3 or Q bar 1. Right. So, continuing on here. Now with this being a 1, we are going to toggle that. And now we don't have any toggling going on. Oh, wait, hold on. These are based on Q2, so we have to figure out Q2 first. Great. So Q2 with 1 and 1, this is going to toggle. Okay. And now we've got J2 based on either Q3 is true or Q1 is false. Q1 is false, so that's going to be good. We can go ahead and fill this in for every time Q1 is false. And yeah. And now that'll help out here. So great. Okay, so with J2 equal to 1 and K2 equals 0, we're going to flip this up to a 1. And now that means we were at zeros, so we're not going to toggle this state. We keep that as a 0. So let's see. This is a situation where we don't have Q3 equal to true, and we don't have Q1 equal to false, which means we're going to get 0 for that J value. And now we've got 0, 1, so we're toggling Q2 back to 0. And have we repeated yet? Have we got back to the original state? So let's check. The original state was 0, 0, and 0. And then we went to 0, 1, 1. And then we went to 1. This one right here, 1, 0, 0. And then we went to 1, 1, 1, and then we went to 0, 0, 0. So actually right here, we went back to the original state. So we know that since we got back to the original state and this stuff only depends on itself, after this, it's all going to repeat. So from that 0 state, we can continue that forward. Great, and there you have it. So the next part is to figure out what's going on with this set up right here with the last flip-flop. So this flip-flop can only ever trigger when Q3 changes from a 1 to a 0. So we need to figure out what the state of J and K were just before that. So K4 is always a 1. J4 is equal to, maybe we'll De Morgan's law this too. So that's Q2 or Q1 bar. And so that means Q2 has to be equal to true, or Q1 has to be false. So Q2 is true, so this is a 1, which means we are going to toggle this. And now that's a 1 until the next time Q3 goes from 1 to 0, which is right here. So we'll figure out what's going on with J4 in this instance. J4 is equal to either Q2, which by this point is a 1 again. And so that means we are going to toggle. So we jump back down to 0. And there's the full repeat cycle. So so if we consider the state that we are in total, we go from a state of 0. So this is originally 0, 0, 0, 0. Then we go up to 0, 0, 1, 1. So I'm just looking at the Qs. Maybe we'll make that a little bit more obvious by changing their color. I've got a macro that turns things into this kind of cool, really jarring color, and that'll make that stand out. Okay, so we go 0, 0, 0, 0 to 0, 0, 1, 1, and then we go 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 1, 1. So this kind of counts regular in binary, except it always moves Q1 and Q2 together. All right, now that is not quite a timing diagram. This is a list of, this was just some rough algebra that we did in order to figure out what's going on. So we can talk about the state. State transition is 0, 0, 0, 0 to 0, 0, 1, 1 to 0, 1, 0, 0 to 0, 1, 1, 1 to 1, 0, 0, 0. And then that goes on 1, 0, 1, 1, 1, 1, 0, 0, and 1, 1, 1, 1 before it repeats 0, 0, 0, 0. So there's our state transition diagram. Now, if we had easy 3D drawing, then we would just draw this going back to the beginning. So this is trying to say that we've gone back to the start. It doesn't repeat, right? So let's talk about timing diagrams. How can we make a timing diagram? We can make a timing diagram actually also in Excel by drawing out different borders. So let's look at how we might do that. So we'll just grab a border drawing tool here. So if you go into, if you go over to this and then borders go, where's that? Draw border. Yeah. So if you go to draw border, then we can click on the bottom like that. Yeah. And then continue that along. And once you've got a few of them, you could sort of copy and paste that over to the rest of the stuff. So we're going to make this stop at a 0, and that should draw the border in. Okay, yeah. And then we can do the same thing over here. 0, 1. It's a bit hard to see, but it should be drawing that border. Maybe we'll get rid of that color. Yeah. So now we've got, maybe we'll draw a bit more. So we'll take the part that repeats from 1s and then down to 0. There we go. Oops. Did not actually work. It's missing some tops on that 1. And that might be because the border viewed itself as being associated with the bottom cell. So let's see if that's fixed it. No. Okay. Well, what you can do is include some extra stuff there. Great. That'll do. Now we need 0. We need the next Q thing. So that's 0, 1, 1. So we'll draw some border for this. 0, 1, 1. You can click and drag too. Yeah, and then this one just continues. So in fact, actually, we could have just copied the previous one for that. So let's go from there over to there and paste. Great. And next one. Oh, that wasn't Q2. That wasn't Q2 at all. But actually, it's the same. So why don't we draw from there and, oh, that didn't work. Let's paste formatting there. Okay. We were pasting the formulas that we had for K2, and that messed things up a bit. All right. Next thing, gonna draw some zeros for that, some ones, some more ones up there. Might be hard to see behind the printing thing. So it is there, it just disappears from the print preview. And draw that over. You can copy and paste the formatting once you've got it, or you can just continue to draw like that, no problem. And then here we've got all 0, 1, all 1, going down to 0, and 0 before going back up after that. Okay, so now here is the skeleton of a timing diagram. So let's copy all of that. Let's paste that down there. And then we'll get rid of the stuff that we don't need. So we don't need the J2. We don't need this J3, K3 stuff. Maybe we should copy it like this instead. Yeah, that's a bit better. And we don't need this J4, K4 stuff. And then if the drawing inside here is confusing, so all of the numbers inside of this are confusing. Oh, we don't need a K2 either. So that's gone. Yeah. Then what you can do is remove the numbers just by selecting everything and hitting delete. So now we're left with a beautiful timing diagram that we got to think through in numbers, which is a little bit easier to type. So we can type something down and then check it. You could even type in formulas for Boolean expressions that are going to evaluate to giving you 1 and 0 if you want to get fancy about it, and then come up with a timing diagram like so. Okay. So here is our timing diagram. When you have timing diagram questions, how far do you have to continue it? Basically until it repeats. So we've got a situation where we start at all zeros, and then we have gone back to 0 right here. So up to here would be fine for the timing diagram. You don't have to continue it beyond that. All right, so now let's build this thing in Multisim. So if we go back up to our circuit diagram there, we've moved it over to one side a bit, just to give ourselves some room. Maybe we can try to make that a bit smaller to fit it all on one page, more or less. Yeah, that looks okay. So we are going to need 4 different flip-flops. Why don't we get that? So we'll add in, looks like HC, so we're at the CMOS part of it. So CMOS and 6 volt, CMOS 6 volt. Get rid of the any sort of search that you've got going on. That'll stop you from seeing the parts. And we need the 109. If we can search star 109. Ah, yeah, it works on that syntax. Okay, 109 N, and there we go. So 1, and we can get a little bit of numbering on the things by just copying and pasting them. So this is going to be 1, 2, and we'll need a bit more space than that. So let's try 1, 2, 3, and 4. Okay. And then we're going to need, what are we going to need? How about we put it like this? That might be a better way to look at things. It's not really a great angle where we can fit everything on the screen at once here. So there's the flip-flops. Then we're going to need to tie the top of them to high and also the bottom of them to high. Now we can modify what's on the circuit diagram a little bit, so we don't need to have exactly a 6 volts with a ground there. We can put instead just VCC, and this is going to be a global connection there. So we'll go VCC and connect that up to the top. Same thing for these other ones there. So don't reset. Connect it up like that. Yeah, that's good. Then we can have, what else are we going to need? We're going to need a ground. And that's like this. And where do we need the ground connected? We need the ground connected to, let's say, K1. K1 bar there. So that's good. We can connect that up right now. We're going to need this in some more places. I'm just connecting it to something for the time being. And we're going to need some LEDs and resistors. So we need 470. Let's see if we can scroll down here. 470. Oh, wait a minute. What am I doing here? Let's just pick any resistor here. Ooh, that's a complicated one. So resistor 1K, and we'll go and paste that. Then we can just change that around to 470. All right, yeah. So we're going to need that hooked up to the LED. After all of the inputs, and we're going to need the LED board. Yeah, so we need a bar, LED red 4, that's good. Place that down there. We need another ground on the other side of that. So this ground we can put there, and then wire those up. Maybe zoom in so we can see. Click a little bit more accurately there. Okay. So that's great. Then we'll connect up from a resistor to each one of the outputs of the flip-flops there. So we need, let's see, number 4 there to be connected up to the most significant bit. We need number 3 connected up to the second most significant bit. Number 2 connected up to the second least significant bit, and number 1 connected to the least significant bit. Oh, then placing 2 to that queue, 3 to that queue, and 1 to that queue. Then what we need is to hook up, let's see, we need a VCC for the don't clear at the bottom there. And we'll wire those guys up together. So you can imagine that this is maybe your bottom rail, or, well, I guess it depends on one of these flip-flops would be on one side of the chip and the other one's on the other side. So still, we've got 2 different rails of voltage there. Now, next thing we need is we need some gates. So we're going to need NAND gates, and the NAND gates are the 0 zeros. So we'll get rid of this search. We'll go all the way up to the top. There we go. And sure. So there's a gate, and there's another one. Let's see. So those gates connect up to this one. We're going to connect the outputs because we can wire these up too. So let's wire that Q bar to that K bar. This one goes over to the clock. I find it easier typically to think in terms of inputs. So we'll check that all the inputs work on all the different things. And as long as everything has the input from the right thing, then it must everything must be all hooked up correctly. So this K is connected to ground. So we don't need to wire that all the way across like we have in the diagram. We can just make a new ground symbol here. It's going to be a little bit less clutter to do it that way. Then we've got the J4 here goes to that NAND gate. And we're going to need this NAND gate to be hooking up to this input here. That's Q bar 2. Then we need the other one to be hooked up to Q1. Great. So that's solid. That's set up. J3 goes from Q3. Over here, we're at J2. That is hooked up to the other NAND gate. And the inputs of that look like they are hooked up to Q3 bar. And also hooked up to this Q1. Yeah, great. Okay, it looks a little bit different than it did up there because the wires are routing differently, but that's okay. Then what do we have here? For K2 bar, that's just hooked up to Q1 bar. And J1 is wired up to high. So let's check. We've got our J and K hooked up from this one to high and ground. We've got J and K hooked up for this one to the output of that gate and to the Q1 bar. And we've got J and K hooked up for this one, J and K hooked up for this one. So this one they're hooked up to just the previous Q's and Q and Q bar. And on this one, they're hooked up to the NAND gate, which is feeding off of Q1 and Q2 bar. And they're hooked up to, and the other one is ground. All right, so that's it. We have everything except for the clock. So for the clock, what we can do is go into a power supply. We could use a function generator, but there's also just a digital clock, right? Digital clock right there. So we'll grab that thing and let's see, what can we do? I want to demonstrate how this works a little bit. So we can, I think I'll rewire that in a moment. But for now, let's just hook up the clock and see what happens. So we've got an output, which is flashing. And you might think, wait a minute, this is at 1K. Why can we see some flashing at all? And that's because the simulation doesn't simulate in real time. So suppose we put this down to 2 Hertz. Then we run this. If we look at the bottom here, you can see the time index for the simulation. So 2 Hertz means that it's changing once every half second. But because we have a 50% duty cycle, it's actually going to change once every quarter second between on and off, yeah? Cycle is half a second, but the duty cycle is 50% of that, so that's how often the light is going to change from on to off. Right. Okay, so that's a little bit too slow. So why don't we change that up to maybe 10 times faster than that. Let's try 20 Hertz and see if that's nice and viewable. There, that looks like a good cycling rate that we'll be able to observe visually. Alrighty, so putting this back to what it was connected to, and now we can hook up our clock. So there is the first clock. The first 3 of these are all clocked off of the input. Rather, they're all coming from the digital clock. And that's connected to that. Got to be careful here to hook it up to the right thing. But the last one is clocked differently. Okay. Okay, so we've got our counting working. And yes, that does reproduce what we were seeing from the timing diagram and what we predicted. To make this work, you need to have set the current to 1 mil. If you're at a higher current, then what you might find is that some of the LEDs don't turn on when they're supposed to. But examining the voltage level will show you that it is still going to a high voltage there. So should be going on, just isn't producing enough current to reach the threshold that we've set for the lights. Okay, this last tool is really exciting. So here's the logic analyzer. It's a way to automatically generate a timing diagram using Multisim. So what you do is you hook up the clock. It does have an internal clock that you can use, but we're going to use the external clock. So we'll say that, just use the external clock there. And then what you need to do is wire up the signals that you want to look at. So for instance, suppose you want to look at this one, then we can just hit run here, and we should get, if everything goes well, set to external clock. We did wire up the clock, so it doesn't seem to be working. I wonder what's up here. Clock is wired to that. We wired signal 1 up to this thing. Ah, there it is. Okay, so we've got, I just scrolled around there and got everything back. So here is the timing diagram. So with a clock external pulsing like that, we've got the signal 6 that we have there is pulsing like this. Now, why signal 6? What's the point of that? Well, this actually is what the net name happens to be here. So you can, well, that's a coincidence that it's on pin 6, but this is net name 6. Remember that every wire that you wire up has a net name assigned to it. So we want to call this Q1. And now if we stop the simulation and start it again, it'll say, ah, that's Q1 there. Got it. And that is what we expected for Q1. Let's wire up the other things. So we'll put a wire. Now you have to put them on the top side of the resistors, because if they're on the bottom side, then most of the voltage drop is going to show up across this, and you won't be able to see the signal showing up on your logic analyzer there. Okay, that's that one, and then we'll hook up Q3 and Q4 right there. Then we'll just label those nets. So we'll go properties, Control M. So if you just select the net and hit Control M nominally, maybe not. So we'll just try double clicking on that. Maybe properties, Q4. Ah, great, got it. And then Q3. And Q2. Okay, let's see. So here we go. Yep, Q1 and Q2 are working together, and then when they pulse down, Q3 goes up, and then Q4 after both of those go up. And we return back to 0 here. Yep, got it. Okay, so there is a timing diagram automatically generated using the Logic Analyzer tool from Multisim.